right, we're going to do section 2.1 now, and we're going to talk about rates of change and tangents to curves. So we're going to be looking at the handout from section 2.1, and the first thing we're going to talk about is average rates of change and secant lines. So here's our definition of average rate of change. So average rate of change of a function y is equal to f of x with respect to x over an interval, and we're talking about an interval now, and the interval is going from 2 points from x1 to x2. It's going to be the change of y divided by the change of x is equal, and that's going to be equal to f of x sub 2 minus f of x sub 1 divided by x2 minus x1. So let's draw a picture of that. I have that part there on your notes that says geometrically. It's going to be the slope of the line through those points. So let me draw this picture on this board here. So suppose I have a curve that looks like this, and I want to have one point here that I'm going to call x sub 1, and that's going to be a point on my graph here, and I'll call that point P. And the ordered pair for P is going to be x sub 1, comma, whatever the function value is at x sub 1. So we can call it f of x sub 1. And then let's take another point on the curve here, and we'll call that point Q. And let's call the x value there x sub 2. So Q is going to be x sub 2, comma, f of x sub 2. So then in the text box there, it says that in geometry, a line joining 2 points of a curve is a secant to the curve. So let's draw a secant between these 2 points here. So that's going to be our secant. Secant is just going to be a line that connects any 2 points. So then it says the average rate of change of f from x1 to x2 is going to be the slope of the secant line. So we're looking at this interval from x sub 1 to x sub 2, and we're going to take the slope of that secant line. So the way that we find a slope of a line is going to be the change of our y values divided by the change of our x values. So here's going to be our change of our y, and here's going to be our change of our x values. So this is where the formula above comes from. So we know that the slope, delta y over delta x, oops, let me fix that delta there. All right, this is, oh, here we go. Okay, so let me write this as delta x. And then looking at the picture, we can see the delta y as the change of the y values from each of those points. So we can write the change of the y values as f of x sub 2 minus f of x sub 1. And then looking at the delta x on our picture, that's going to be the difference in the x values from the picture. So that's going to be x sub 2 minus x sub 1. So that's where that formula comes from. So let's find the average rate of change of the following functions over the given intervals. So we'll add a new page here. So the first one says f of x is equal to x squared minus 2x. And our interval now is going to be from -2 to 1. So remember, this is an interval of x values. It's not an ordered pair in x comma y. It's an interval of x values. So to find our average rate of change on that interval, we're going to find the slope of the secant line that connects those 2 points with those 2 x values there. So we have f of x sub 2 minus f of x sub 1 divided by x2 minus x1. And now we're going to fill in our x sub 1 and our x sub 2. So here in this example, we can say that -2 is our x sub 1, and 1 is going to be our x sub 2. So we're going to fill those values into this formula. So we have f of x sub 2 is 1, minus f of x sub 1 is negative 2. And that's going to be divided by x2, which is 1, minus x sub 1, which is negative 2. So we have 1 minus negative 2 in the denominator. Now we have to find f of 1 and f of negative 2. So we can continue this and write that, or we can do those calculations off to the side. So what we want to do is we want to find the function called f, and we want to plug 1 into the function, and then we're going to find the function f again and plug negative 2 into the function. So let's do that. So when we plug 1 into that function, this function here, we're going to go back to this function, we're going to plug 1 in here. We get 1 squared minus 2 times 1, and then we have minus, and now we're going to plug negative 2 into that function. We have to be careful with this minus sign in here. So we're plugging negative 2 in, we get negative 2 squared minus 2 times negative 2. And then we're going to divide that whole thing by 1 minus negative 2. So we're going to divide that by 3. So that'll be 1 plus 3. All right, so then in the numerator, let's simplify this. First of all, we have 1 minus 2, so that's going to be a negative 1, minus, and then in this bracket we have 4 plus 4, and that whole thing is divided by 3. And then we have negative 1 minus 4 plus 4, so that's negative 1 minus 8. And dividing that thing by 3, we get negative 9 divided by 3, and that's going to be equal to negative 3. So the average rate of change of this function, this is going to be a parabola if we would graph it, between the x values negative 2 and 1 is going to be negative 3. So the slope of that secant line in that interval is going to be a negative 3. All right, then let's look at example B. And this one says f of x is equal to the sine of x. And now we're looking at the interval from 3 pi over 4 to 4 pi over 3. All right, we're going to do the same thing that we did before. We're going to find the slope of that secant line between those two values of x. So f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. All right, so let's plug our x sub 2 and our x sub 1 in. So just like before, let's call one of these values x sub 1 and let's call the other one x sub 2. So we're finding f of 4 pi over 3 minus f of 3 pi over 4. And then we're going to divide that by x sub 2, which is 4 pi over 3, minus x sub 1, which is 3 pi over 4. All right. So first of all, we have to find f of 4 pi over 3. And that's going to be the sine of 4 pi over 3. So I'm going to take that function f and plug in 4 pi over 3. So we're looking at finding the sine of 4 pi over 3. And then we're going to subtract that from the sine of 3 pi over 4. Because we have to plug 3 pi over 4 into that function f. And then we're going to divide that by, and we have to do the difference, 4 pi over 3 minus 3 pi over 4. So we need a common denominator in order to do that. So the denominator is going to be 12 for each one of those. So to get a 12 in that first denominator, we have to multiply the top and the bottom by 4. So the first one is going to be 16 pi over 12. And then for the second one, for this one here, to get a 12 in the denominator, we have to multiply the top and the bottom by a 3. So this one becomes 9 pi. over 12. All right, so now we have to think about the sine of 4 pi over 3. So sine of 4 pi over 3. So 4 pi over 3, we can think of that as, that's going to be 1 1/3 pi. So we know that to get to the pi is 180 degrees, so we want 1/3 more. So 4 pi over 3 is going to be down here in the third quadrant. The reference angle is going to be pi over 3. So our reference angle is going to be pi over 3. So the sine of 4 pi over 3 is going to be the same thing as the sine of pi over 3, except we just need to check the sign to make sure, see if it's positive or negative. In the third quadrant, sine is going to be negative. So this angle, our angle theta, then is going to be a negative root 3 over 2. So sine of 4 pi over 3 is going to be negative root 3 over 2. All right, then we have to find the sine of 3 pi over 4. So let me erase this here so I have room to write this. All right, so we're looking for the sine of 3/4 pi. So draw a picture again. So 3/4 of pi is going to be in the second quadrant. Our reference angle is going to be pi over 4. So our ref theta prime is going to be pi over 4. So the sine of 3 pi over 4 is going to be the same as the sine of pi over 4, except we just want to make sure the sign, check the sign whether it's positive or negative. Sine is positive in quadrant 2, so the sine of 3 pi over 4 is going to be positive root 2 over 2, same as the sine of pi over 4. So this is going to be minus root 2 over 2. And then that's going to be divided by, now we can do that subtraction since we have a common denominator. And 16 pi minus 9 pi is going to be 7 pi over 12. All right, let's do the subtraction in the numerator. And negative root 3 minus root 2 is going to be, I'll do that down here. That'll be negative root 3 minus root 2. And that's going to be over 2. And then that whole thing is going to be over 7 pi over 12. All right, so we have a fraction in the numerator, fraction in the denominator. So to do that division, we're going to change that to multiplication and then just flip that denominator. So we have negative root 3 minus root 2 over 2 times 7 pi. Oops, I got to flip that one. Times 12 over 7 pi. And we'll see if there's anything to simplify. We can divide a 2 out of the numerator and denominator. So we can cancel this 2 here and cancel a 2 there, and we're left with the 6. So in the numerator, we're left with 6 times negative root 3 minus root 2 divided by 7 pi. And then that's going to be our final answer. We can't cancel anything else out or do anything else to that one. All right, so let me get another page here. And I'm going to talk about Galileo's law of a falling object. This isn't in your notes that I gave you, so you can write this on a separate sheet of paper. So Galileo's law of falling objects. All right, so we're going to talk about free fall. And this is when we're talking about an object that's dropped from rest. And Galileo said that an object that's dropped from rest will fall at a distance that's proportional to the square of the time that it falls. So what he was saying is that y is going to be equal to 16t squared. So y is going to be the distance of the object fallen after t seconds. So t is the number of seconds, and then y is going to be the distance that it's fallen. So y is going to be proportional to the square of that time. And this constant of proportionality is the 16, so that's going to be a constant that will always be in there. So here's an example. Let's find the average speed of an object that's dropped from a certain height during the first 2 seconds. Okay. So if you're dropping an object and you're finding the average speed during the first 2 seconds, you're starting with the time being 0, and then you're ending at the time being 2. So this is, our interval is going to be from 0 to 2 seconds. So we're finding the average rate of speed here, so we're going to use our same formula that we had before for the average rate of change, which is f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. All right, so we're going to find our function f. Our function f is going to be this function right here. So I could write this as I could write this function as f of t. Instead of calling it y, I can call it f of t is equal to t squared. And I have the variable t here instead of x over here, but I could have made these t sub 2 and t sub 1. All right, so then we're going to take x sub 2, and x sub 2 is going to be 2. So we're finding f of 2 minus f of 0. And that comes in our interval. This is going to be our x sub 2, x sub 1, and then this will be our x sub 2. And then we're going to divide that by x sub 2 minus x sub 1, which is 2 minus 0. All right, so we're going to take our function f and we're going to plug 2 into it. So 2 will be our variable. So then we have 16 times 2 squared, using our function, minus 16 times 0 squared divided by 2 minus 0, which is 2. And then let's evaluate that. That'll be 16 times 4 minus 0 divided by 2. And that's going to be 64 divided by 2, and that ends up being 32. And that's going to be feet per second. All right. So let's do one more example. So again, using Galileo's law, let's see what happens from second 1 to second 2. So now our interval is from 1 to 2. All right, do this the same as what we did before, but now we're going to plug in 1 for x sub 1 and 2 for x sub 2. Our interval this time is going from 1 to 2 instead of from 0 to 2. So this is going to be 16 times 2 squared minus 16 times 1 squared divided by 2 minus 1. And that's going to be 16 times 4 minus 16 divided by 2. So that's going to be 64 minus 16 divided by 2. And then that's going to be equal to 48 feet per second. So what we're trying to do here is we're calculating the average rate of change, or the average rate of speed of a fallen object on an interval, but what we want ultimately to be able to do is to find the speed of a falling object at a single instant instead of looking at this interval. We want to find out, for any given value of x, what is going to be the speed of that falling object at that specific instant. So we want to find the speed of a falling object at a single instant x sub 0 instead of using an average. Because our average rate of change that we've been calculating is an average in an interval, but we want to find that speed at a single instant. So to do this, we're going to calculate the average speed over shorter and shorter time intervals. All right, so let's do that. So let's look at different intervals here, and this will be the length of the time interval. And we're going to be starting at 1 second, and then we're going to calculate the average speed starting at x sub 0 is equal to 1. So for the first one, we're going to start at 1 and we're going to go to 2. So in this one, the length of our time interval is going to be 1. And then we're going to make these intervals shorter and shorter. So let's start at 1 again. But instead of that entire interval being 1, let's make it 0.1. So let's go from 1 to 1.1 and then see what happens. And now the length of our time interval is going to be 0.1. And then let's start at 1 again, and let's go to 1.01. So now the length of our time interval is 0.01. And then we can keep going. Start at 1 and we go to 1.001. So the length of our interval now is going to be 0.001. And we can continue this, and again starting at 1, go to 1.0001. 0001. So we can keep making those time intervals get closer and closer and closer. Those x values, that the interval is going to get smaller and smaller. And we're going to calculate the average speed, again starting at 1 for each one of these. So for the first one, we're calculating the average speed from 1 to 2. We're still using that same formula that we used on the last page, f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. That's our average rate of change. So that's our average speed here in this example. So we did this one up above. That was in the last example that we did. So when we had a length of the time interval from 1 to 2, we already found out that the first one is going to be 48. We just did that calculation above, so we don't have to redo it. So for the next one, when we're going from 1 to 1.1, our interval now, our x sub 1 is 1 and our x sub 2 is 1.1. So what we're finding for this one is f of 1.1 minus f of 1, that's our x sub 1, divided by 1.1 minus 1, just like we were doing in the last couple of problems. We're using the same function here. The function still is our f of t is equal to 16 t squared, or we can call it x squared. So whatever our variable is. So we're taking 1.1 and we're plugging it into this formula. So we have 16 times 1.1 squared minus 16 times 1 squared. And then we're going to divide that by 1.1 minus 1. And then if you put that into your calculator, do those calculations, this one ends up being 33.6, and that's going to be feet per second. And then go ahead and do the remaining 3 that are on this chart. All right, so when you did the remaining 3 calculations, as that interval kept getting smaller and smaller, doing those calculations the same way, you should have gotten 32.16, then 32.016, 32.0016. And you can see then, as we keep making the intervals smaller and smaller and smaller, it appears that there's a limiting value here, that all of these values are going to be approaching 32 feet per second. Because you can imagine that the next one is probably going to be 32.00016. And then we can keep going, and it's going to get closer and closer to 32. So let me write that down. So the average speed, starting at, and for all of these we're starting at the same value. So starting at x sub 0 is equal to 1, seems to approach a limiting value of 32 as the interval decreases. So let's confirm this algebraically. So we have f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. And let's take a look at a quick picture over here again. So if this is our x sub 1, this is our first point, x sub 1. And then let's say this is our second point, x sub 2, that makes up our interval. Remember, this point here was x sub 1 comma f of x sub 1. And we wanted to look at these, the change in this y value divided by the change in the x value. But what we're doing is we're making this interval shorter and shorter and shorter. So this delta x that we had before, now we're going to just call it h. And we're going to make that h get really, really small, because we're going to bring this x sub 2 closer to the x sub 1. So that was our whole intent here. So now the difference between x sub 1 and x sub 2, we're going to call that h. So instead of writing this as x sub 2 is the same thing as x sub 1 plus h. So we're starting at x sub 1 and we're just adding that little bit h to it. So instead of writing f of x sub 2 here, I'm going to write f of x sub 1 plus h minus f of x sub 1, and we're going to divide that by x2 minus x1. So what's x2 minus x1? Looking at our picture, the difference between x2 and x1 is just our h value. So in the second formula that we have here, we don't need to have an x sub 2 value. We just need an x sub 1, and then we're going to call it h. So this is the same thing. If we're starting at, and I really should have written this as x sub 1, I guess. Our starting value, x sub 1, is 1. So we're finding f of 1 plus h, because x sub 1 is 1, minus f of 1 divided by h. Okay, then we're going to go to our function, f of x again. Remember, we're using the same function. So f of t, or f of x, was remember that was 16t squared. So same function that we've been using. So now we're going to take 1 plus h and plug it into that function, and we get 16 times 1 plus h, and we have to square that. Minus f of 1, and when we plug 1 into the function, we get 16 times 1 squared divided by h, and this is equal to 16. When we FOIL 1 plus h, we get 1 plus 2h plus h squared minus 16 divided by h, and distributing that 16, we get 16 plus 32h plus 16h squared minus 16 divided by h. So the 16s are going to cancel. We have 16 minus 16 in the numerator. And then all of the rest of the terms all have an h in them, so we can factor an h out of the numerator. And we get h times 32 plus 16h. And we're going to divide that by h. And the h's cancel. And we have 32 plus 16h. So then we said before that the limiting value was 32, and we can see why that's true, because as we make h small, so as we, let me go to a new page here, otherwise it's too crowded there. So we have 32 plus 16h, so as h gets smaller and smaller, so we're getting really close to 0, but not exactly 0, so we're getting h to be 0.00001, something like that. As h gets really, really small, the limiting value, or the value of this function, approaches 32 feet per second. All right, so that comes from Galileo's law. All right, then we're going to go back to our notes for this section. And we're going to define the slope of a curve. So what is meant by the slope of a curve at a point P on a curve? So now we're talking about a specific point and not an interval on a curve. So if there is a tangent line to the curve at that point, and that's going to be a line that just touches the curve, like the tangent to a circle, we can identify the slope of the tangent as the slope of the curve at P. So if we have this circle here and we have a radius here, this is going to be an example of the tangent to a curve at that point P. So we're going to say that's a point P, and this is going to be a 90-degree angle. And then the tangent is just going to be that line, and that's the line that we're going to find the slope of. So a line L is going to be tangent, so this will be our line L. It's going to be tangent to a circle at a point P if it passes through P and it's perpendicular to the radius at P. So here's our radius, and that radius is going to be perpendicular to that tangent line. It's going to create a 90-degree angle there. So to define tangency for curves, so we're going to start with the slope of the secant PQ, and then we're going to look at limiting value of the secant slope as Q approaches P along that curve. So I'm going to draw that on this other screen here. So suppose we have a curve, and this is the curve that's drawn on your sheet, and we have a point P here, and then let's say that this is going to be a point Q. And first of all, we're going to start with the slope of the secant, which is going to be the line that goes from P to Q. So we can draw a line from P to Q like that. And then we'll be finding the slope of that line. And then what we're going to do is we're going to look at the limiting value of the secant slope as Q approaches P along this curve. So we're going to take Q and we're going to move Q closer and closer to P along that curve. So maybe at some point Q is going to get to this point here on the curve, and then we can look at the slope of that secant, and then maybe another point that's right here, and we can look at the slope of that secant, and we can just continue to get Q closer and closer and closer to P, and we're going to be looking at all of those secant lines. All right, so that's just the general concept. So we're making that second point get closer and closer and closer, until it's really super close. So in the example, let's find the slope of y is equal to x squared. And we're going to do this now at the point 2, 4. So now we have a point, we have an x, y value, and we don't have an interval like we did before. We're not going from x sub 1 to x sub 2. We're looking at a specific point. And then we're going to write the equation for the tangent at this point. So let's draw a picture of this. All right, so this is the function y is equal to x squared. So when our x value is 2, our y value is going to be 4. So our point right here is 2, 4. So we want to find the slope of that curve at that specific point. So we're going to use our secant slope. And remember, our secant slope is our delta x over a delta y. So we have f of x sub 2 minus f of x sub 1 divided by x sub 2 minus x sub 1. But we don't have a second point in this case. We're only given that 1.2, 4. So what we want to do is that same concept. We want to have another point over here, but we want to make that point get really close to 2. And so we're going to call this point 2 plus h. So just like with the Galileo's law problem, we're going to take that h value and make it really, really small. And we're going to add that really small value to 2. All right, then to calculate the slope, we're going to do it just like we did before. So the change in these different x values here is going to be h. Okay. All right, then just like we did in the last example, x sub 2, we're going to call f of x sub 1 plus h. So whatever this first value is, we're going to take that value and we're going to add h to it. So if this was our x sub 1, remember this was our x sub 1 plus h minus f of x sub 1, and we're going to divide that by h. The difference in x sub 2 and x sub 1 is going to be our h value. All right, so here with this point 2, 4, we only have one x value, right? So this is going to be f of 2 plus h, as our x value is 2, minus f of 2, divided by h. And now we're going to take 2 plus h, we're going to plug it into our function f. So our function f is this y is equal to x squared. We could write it as f of x is equal to x squared. So we're plugging 2 plus h into that function, and we get 2 plus h squared minus f of 2 is what we get when we plug 2 into that function. So minus 2 squared. And we're going to divide that by h. All right, let's FOIL 2 plus h. When we FOIL 2 plus h squared, we get 4 plus 4h plus h squared minus 4 divided by h. The 4's are going to cancel, they become 0. And we get h, 4h plus h squared over h. Everything has an h, so we can factor an h out of the numerator and get 4 plus h divided by h. These h's cancel, and we're left with 4 plus h. Okay, so now we're going to look at what happens as that h gets really small. So as h approaches 0, so I'm going to write it like this. As h approaches 0, that means that h is going to get really, really small, just like before. This is our slope. Remember, this is our delta y over our delta x. That's our slope. And we're looking at the slope of this curve at this specific point in this example. We're looking at the slope at this specific point. So the slope is going to be equal to 4. So the slope is going to be equal to 4 as h gets really, really small. All right, so now we need to write the equation of that tangent at that point. So looking back at this picture, at this specific point right here, that red line that I drew, that's our tangent line at that point, and we want to write the equation of that line. So in order to write an equation of a line, if we have a slope, so write equation of tangent line. So what we know is that the slope is equal to 4, and then we know that we have that point 2 comma 4. So we can use the point slope formula. And we can do that since we have a slope and we have a point. So the point slope formula says y minus y sub 0 is equal to m times x minus x sub 0. So let's plug that information in. So this point is going to be our x sub 0 comma y sub 0. So we have y minus y sub 0 is 4, m is 4, x minus x sub 0 is 2. So that's the equation in point slope form. And if we want to put it in a slope intercept form, we can solve for y. So slope intercept, we need to solve for y. So this one is point slope form. So solving for y, we get y is equal to, I'm going to add 4 to both sides. And over here, I'm going to distribute that 4 and get 4x minus 8. Then I'm going to add that 4 over here. So y is equal to 4x minus 4. Okay. So this is going to be the equation of the tangent line at that point 2 comma 4 from our previous picture. All right, then we have one more problem in this section. So go ahead and try this one on your own. I'll pause this. So find an equation of the tangent line to y is equal to negative 1 minus 2x squared at the point negative 2 comma 9. So try that one on your own. All right, I just got this problem started so you can follow along and check your work for what you have done so far. So here's our equation. This is our f of x, and I could write this as f of x instead of writing it as y. And we have that's negative 1 minus 2x squared, and we're looking at that specific point negative 2 comma 9. So that's our x and our y value. So we're going to use this f of x plus h minus f of x divided by h. And it doesn't matter if I call it x sub 1 here because I only have one x value in this formula. So I'm taking my x value, which is negative 2, and plugging it into that formula for the second step. And now what I have to do is find f of negative 2 plus h minus f of negative 2. So I'm going to do that off to the side because it's a little bit more of a calculation than it was before. F of negative 2 means I'm going to find the function called f, which is this function right here, and I'm going to take negative 2 plus h and plug it in there for x. And that's what I showed here in this step right here. And now I have to simplify this. So I have negative 1 minus 2, and then you should have squared the negative 2 plus h, so FOIL that out. And when you did that, you should have gotten 4 minus 4h plus h squared when you FOIL that. And then we have to distribute that minus 2. So that's equal to negative 1 minus 8 plus 8h minus 2h squared. And that's going to be equal to negative 1 minus 8 is minus 9 plus 8h minus 2h squared. So that takes care of the first part over here, this f of minus 2 plus h. So let's do the second part and let's find f of negative 2. So now we have to take negative 2 and plug it into our function f, everywhere we see an x. And remember, that's the function up here. So that's negative 1 minus 2 times negative 2 squared. And that's equal to negative 1 minus 2 times 4. And that's equal to negative 1 minus 8, which is equal to negative 9. All right, now that we have those two pieces done, we can continue over here. We found f of negative 2 plus h. That's negative 9 plus 8h minus 2h squared minus f of negative 2, so we have minus negative 9, and divide that whole thing by h. So this is negative 9 plus 9 at the end, so those are going to cancel out. And then we have 8h, oops, that's minus. So 8h minus 2h squared divided by h. Factor out an h just like we've done every time. And we have 8 minus 2h divided by h. H's cancel, and we're left with 8 minus 2h. So then you can see, just like before, we're going to look at making that h really, really small. And we're going to say that as h gets really small, as h approaches 0, so h is going to be really close to 0, this is our slope. This whole thing here is what we're doing to find our slope. That's our rate of change. Our slope is going to be equal to 8. And then we can write the equation of this line. So equation of the line that's tangent to the curve at that point. So equation of the line tangent to y is equal to negative 1 minus 2x squared at the point negative 2 comma 9 is, and again we'll use that point slope formula, y minus y sub 0 is equal to m times x minus x sub 0. Point slope form, since we have a point and we have a slope. So we already found out that our slope is 8. So filling in the pieces, we have y minus our y sub 0. Remember, this is our x comma y. Our y is 9. Slope is 8. X minus x sub 0, x is negative 2. So this is going to be y is equal to, let me change that to a plus. Y minus 9 is equal to 8 times x plus 2. Now we're going to add that 9 to both sides and distribute that 8. So we have y is equal to 8x plus 16 plus 9. And then y is equal to 8x plus 25. So that's the equation of the line tangent to that curve, negative 1 minus 2x squared, at that specific point, negative 2 comma 9. And that's it for section 2.1.